All right, welcome to the deep dive. Today, we're going to try to tackle a question that honestly kind of feels like it's straight out of science fiction. But the thing is, it's actually coming from like real cutting edge research.
Oh, absolutely.
So imagine, right, we've got these like two artificial intelligence scientists, and we take these AI scientists and we train them on the exact same scientific problem.
Mm-hmm.
Would they both come to the same fundamental understanding of how things work?
Right.
Would they build like the same theories?
Yeah.
Or is it possible that they could actually end up with like totally different but still, equally valid ways of explaining like the entire universe?
It's a really deep question. It kind of gets at the heart of like what intelligence is and what scientific discovery really is. And it's becoming, increasingly relevant now with AI being used in all sorts of fields. Like it's peering into the tiniest particles, charting the cosmos, even designing new materials. And it's not a huge leap to think that maybe one day AI could be like independent scientists making their own discoveries.
Yeah, it's so true because you're right. AI is popping up all over the place in all these scientific fields and is kind of a natural next step to think, well, what if we let AI do all the science?
Right, exactly.
And that's what we're diving into today, just for you, listener.
Exactly, that's what we're looking at.
We're going to see if these AI scientists, when they look at the same evidence, do they come up with the same explanations? Or do they go off in a million different directions and maybe even come up with conflicting ideas?
Yeah.
And the thing is, we actually have some really surprising findings, so stick with us.
Yeah, this is going to be good.
We're going to try to make this understandable.
Yeah.
And we're not going to get bogged down in super technical details.
Absolutely not. We want to make this as accessible as possible.
All right, so to help us go on this exploration, we're looking at this super interesting paper.
Yeah, this is a great paper.
It's called Do Two AI Scientists Agree? And it's by Xinghong Fu, Zheming Liu, and the amazing Max Tegmark from MIT.
Yes, the one and only.
And this was just published on April 4th, 2025, so hot off the presses.
Very recent.
So what is this paper actually about?
Well, this paper introduces this really cool new type of AI called MASS.
Okay.
And it stands for Multiple AI Scalar Scientists.
Right, Multiple AI Scalar Scientists.
And basically what the researchers did was they used these MASS networks to kind of, study different physics problems.
Yeah.
And then they looked at the theories that these AI models kind of came up with. So it's a really unique window into how AI might understand, the world around us.
So AI learning about physics?
Exactly.
And then coming up with its own theories.
Yeah, essentially doing science.
Okay, and this paper, they're trying to answer some pretty compelling questions.
Oh, yeah, absolutely.
So, when these AI scientists work by themselves on the same problems, will they come up with, a single unified understanding?
Right.
Or are we going to see a bunch of different explanations that might even disagree with each other? And then maybe the most important thing is, will we even be able to understand the theories that the AI comes up with?
Right. Can we even make sense of them?
Okay, so let's start looking at their experiments. What was the first thing they did?
So they started with, one AI scientist, one single MASS network, and they had it try to learn about a very basic system, the simple harmonic oscillator.
Okay, the simple harmonic oscillator. Now, I remember this from physics.
Oh, yeah, this is Physics 101.
It's basically like a spring,
yeah.
And you attach a weight to it, and the weight bounces up and down?
Exactly. Just a mass on a spring oscillating back and forth.
Okay, so what's so interesting about that?
Well, here's the thing. Even for something as simple as, a mass on a spring, there's not just one right way to describe it mathematically. You have, Newton's laws, which focus on forces. And then you have, Hamiltonian mechanics, which looks at the energy of the system. And both of these are totally valid ways to understand the same motion.
Got it.
So it's kind of like having two different maps of the same place.
Okay.
Newtonian mechanics might focus on the roads.
Okay, rows.
Right, forces. And Hamiltonian mechanics might focus on, the elevation.
The elevation.
The energy levels.
Okay.
And both can get you to the same place, but they describe the journey in different ways.
Got it. So, two different perspectives on the same physics.
Exactly.
So what happened when they trained their MASS network on this bouncing spring?
Well, first off, MASS actually learned to predict how the system would behave really well.
Okay.
With very little error.
So it learned it.
It learned it.
It could predict what was going to happen.
Yeah, it got it. But here's where it gets really interesting. They wanted to see how, like, the model's theory, how it was explaining it to itself, how that evolved during training.
Okay.
So they looked at the number of significant connections in its final layer.
Okay.
So you can kind of think of these connections as like the building blocks of its understanding.
Okay, yeah.
And even after all the training was done, it still had a surprisingly large number of these connections active, like around 42.
42.
42.
That's way more complicated than just saying, like, force equals mass times acceleration.
Right.
Or whatever the energy equations are.
Right. You would think it would be simpler.
You would think, yeah.
Yeah.
So it had 42 of these things active.
42 active connections, yeah.
Okay, so was it still able to, like, accurately simulate the oscillator, even with all that complexity?
Yeah, so that's the crazy part.
Okay.
Even though it seemed really complicated, MASS was still able to accurately simulate how the oscillator would move over time. Like, it got the predictions right, even if, like, its internal explanation seemed really, really convoluted.
Okay, so it had a really complex way of getting to the right answer.
Yeah.
Interesting.
Yeah.
All right, and then they took this idea even further, right?
They did. So they looked at the specific mathematical function that MASS had learned, which is kind of analogous to like energy and Hamiltonian mechanics.
Okay.
And they compared this learned function to the actual Hamiltonian function for a spring mass system, which, that's a pretty relatively straightforward mathematical expression involving like position squared and velocity squared.
So, like, did the AI basically rediscover the concept of energy in this system?
It kind of got close,
Yes.
but it wasn't a perfect match.
Okay.
So the learned function had a similar overall shape. It was like kind of bowl-shaped,
Okay.
which indicates that there's like a minimum energy state.
Right.
But it also had some key differences. Like it could take on negative values, which isn't typical for energy in this context. And its like detailed shape was a little bit skewed compared to the standard energy equation.
Okay.
So it really highlights that there are lots and lots of ways that an AI could represent a physical system.
Yeah, and this is interesting because it's almost like saying that the AI is like understanding something about the system, but it's not understanding it in the same way that like a human physicist would.
Exactly. It's finding a way that works to predict the motion, but it's not a carbon copy of our like textbook understanding.
Right. Okay, so even though it had these 42, what do you call them?
Connections.
Yeah. 42 connections.
Sure.
That were still active. Does that mean that all of those 42 are like equally contributing to its understanding?
Not necessarily, no.
Okay.
So the strength of the connections gives us some idea of what the model thinks is important.
Okay.
But the actual influence of each connection depends on its activation.
Activation.
Yeah, so you can think of activation as the signal that's passing through that connection. So it's basically, how strong is the connection multiplied by, the value of the information that it's getting.
Got it.
And they actually identified the top 5 connections based on their average activation strength.
Okay.
And also based on just like their raw connection strength.
Okay.
And interestingly, they found a lot of overlap between those two lists.
Oh, okay.
So there are some core connections that were consistently important, no matter how you looked at it.
Right. So that's cool. So we've narrowed it down to like 5 main ones.
Yeah.
But we still got 42 floating around in there.
We do.
So how do we know if this is just like a bunch of random mathematical stuff or if it actually represents like a real theory?
Right.
Even if it's not a theory that we would necessarily come up with.
Right. That's a great question. And that's where this technique called correlation analysis comes in.
Correlation analysis.
Yeah. So imagine you've got like all these different things that are, influencing something, and you want to see which things tend to move together.
Okay.
So correlation analysis helps us to see those relationships.
Okay.
And what they found was really cool. They looked at how the activations of these, important connections were related to each other.
Mm-hmm.
And they found distinct groups of connections where the activations were really highly correlated.
Okay.
And these groups often represented like combinations of like the fundamental properties of the system,
Sure.
like its position, its velocity, and how that learned function changes with position.
Okay.
So what this tells us is that even though it was using a lot of different mathematical pieces, they were often like working together in a coordinated way. It's not just 42 independent ideas floating around.
Got it.
It's more like, different parts of a similar explanation.
Okay.
It's like, you have a complex machine and it has a bunch of parts.
Yeah.
But ultimately, they all work together to do one thing.
So it's still one coherent idea.
Exactly. Yeah.
Okay, so one AI scientist, one complex theory.
Right.
All right, so what happens if you start challenging these AI scientists with more complex systems?
So that's where things get even more interesting.
Okay.
So they trained MASS on a sequence of systems that got, increasingly complex.
Okay.
So they started with our simple harmonic oscillator.
Okay, our spring.
Yeah, our spring, good old spring.
Right.
And then they moved to a simple pendulum, swinging back and forth.
Okay.
Then they did the Kepler problem, which describes how planets orbit stars under gravity.
Oh, wow.
And finally, they did the relativistic harmonic oscillator, which incorporates some of the effects from Einstein's theory of relativity.
Okay, so they started with something easy,
Mhm.
and they just kept making it harder.
They just kept ramping it up.
Okay.
Yeah.
So what happened as these challenges got harder?
Well, if you look at figure 6 in the paper, it shows a really clear picture. You can see that some of these AI scientists, remember, they ran multiple training sessions with different random starting points,
Right.
which they called seeds.
Okay. C's?
Some of these AI scientists actually struggled and failed
Okay.
as the systems got more complex,
Interesting.
which suggests that maybe they learned, the wrong theories.
Okay.
They had theories that worked well for simple stuff.
Okay, but couldn't handle the harder stuff.
But then they kind of fell apart when they had to deal with more complicated scenarios.
Makes sense.
It's like, you learn a rule that works for basic addition,
Yeah.
but then it doesn't work when you try to apply it to fractions.
It breaks down.
Yeah, it breaks down.
Okay, cool.
Yeah.
Now, the paper also mentioned something kind of surprising, that some of the AIs that initially failed, they actually recovered later on.
Yeah, that was unexpected.
How's that even possible?
Well, they think that what's happening is these more complex systems, they impose stricter requirements on the AI. And those requirements can actually help guide a struggling network, back on track.
Okay.
And help it to converge on a more general theory.
Okay.
One that can actually explain a wider range of phenomena.
So it's almost like the more difficult problems, they force the AI to actually learn something more general.
Exactly, yeah. It's like, sometimes when you're doing a puzzle,
Yeah.
having more pieces can make it easier to see how everything sits together.
Oh, I see. So the more pieces you have, the more context you have.
Exactly, yeah, you get more context.
Okay, so encountering more complexity isn't always a bad thing.
No, sometimes it can be helpful.
Okay, that's interesting. And then they also focused on one particular AI, right?
They did, yeah. So they looked at one specific AI scientist. They identified it by its seed number, seed 52.
Okay.
And they tracked how its learned relationships evolved as they introduced more and more systems.
Okay.
So you can see this really well in figure 7. It kind of lays it out visually. And the main finding was kind of twofold. First, as the AI scientists saw more and more systems, the number of distinct, important components in its theory, it actually went down.
Oh, okay. So more data, simpler theory.
Exactly, yeah. For example, it started with around 20 significant components when it was only learning about the simple harmonic oscillator.
Okay.
But this number dropped down to just 6 or 7 components that stayed important across all 4 of the systems.
Wow. So it really learned to focus on what mattered.
Yeah, it was like it figured out, okay, these are the essential things I need to pay attention to.
Okay, so that's one finding, and then the second finding.
Yeah, so the second thing they noticed was that the specific nature of these theories, they actually became more diverse.
Okay, more diverse.
In a certain way, yeah.
How do you mean?
Well, they saw an increasing number of components that weren't very strongly related to each other.
Okay.
So, they identified the specific set of 6 or 7 components that persisted across all 4 systems. And there was a strong emphasis on components related to the object's position, its velocity, and how the learned function changes with position.
Okay. So more diverse components, but still focused on those core properties.
Exactly. And, they even tried changing up the order in which the AI encountered these systems just to see what would happen.
Oh, really? So instead of starting with the simple harmonic oscillator, they started with something more complex?
Exactly. And what they found was if you started with the more difficult systems, the theory that it learned would place a greater emphasis on components related to the velocity and the change of that function with respect to position.
Oh, that's interesting. So, like, the order in which you learn things can actually influence how you understand the world.
It seems like it can, yeah. It suggests that the initial experiences, even for an AI, can influence the way they build up their understanding.
Okay.
But, regardless of all that, the big takeaway from this part of the study was clear.
Okay, what's that?
When an AI encounters a wider range of physical systems, it leads to a simpler underlying theory.
Okay, so more data, simpler theory. That's a good takeaway.
Yeah, it's a good word.
So we've talked a lot about one AI scientist learning about these systems.
Right.
But what about the original question?
Ah, yes.
When you have multiple AIs looking at the exact same problem.
The big one.
Yeah. Do they end up agreeing?
Right. Do they converge on the same understanding?
Yeah.
So to address this, they used, those different random starting points, the different seeds for the mass S network.
Okay, the seeds.
As like stand-ins for different individual AI scientists.
Okay.
So they trained a whole bunch of different mass S networks, and each one started with slightly different random initial settings.
Okay.
And they all learned about the same physical system.
Got it. So, like, each one is an individual AI scientist with its own starting point.
Exactly. Like, think of it as giving them each, like, a slightly different textbook to start with. And the question is, do they all end up thinking the same way?
Right. So did they?
Yeah.
Like, did they all end up with the same internal connections and, activation values?
No, not at
Not
all.
at all.
No. So the paper actually shows this very clearly in figure 13 in one of the appendices.
Okay.
That the specifics of, how they work internally, like the strengths of their connections and their activation values, they differed a lot between the different AI scientists.
Okay, so different internal workings.
Yeah.
Interesting.
But here's the amazing part.
Okay.
The important components that each AI scientist chose to use, they tended to be the same,
Really?
even though the exact amount that they were using them varied.
Oh, okay.
So it's kind of like, different chefs using slightly different amounts of the same ingredients to make the same cake.
Okay, I see. So different settings,
Right.
but the same fundamental building blocks.
Exactly. Yeah. And figure 8 really shows this beautifully.
Okay.
It shows the relative importance of each possible component across 50 different mass scientists that were all trained on the same system.
Okay.
And you can see these clear vertical bands,
Okay.
which show that there are specific components that consistently have a high level of activity across a lot of the different AI scientists.
Okay.
So these are the components that are good at describing the system.
Got it. So they're all kind of zeroing in on the same core concepts.
Yeah, they're all picking out the same important pieces.
Okay, cool. But what about the overall, mathematical functions that they learned?
Right.
The paper mentioned that they could look pretty different.
Yeah, they can.
Okay, so how do we know that they're really getting at the same underlying understanding?
Right. Well, they use this technique called principal component analysis, PCA.
PCA.
Yeah. So imagine you've got a cloud of data points,
Okay.
and PCA helps you find the direction in that cloud where the data varies the most.
Okay.
So it helps you identify the most important underlying pattern. And what they found was that the first principal component, the most important pattern, often explain a huge proportion of the total variation.
Okay.
In many cases, over 90%.
Wow. Okay, so there's a dominant theme
Yeah.
that everyone's picking up on.
Exactly.
Okay.
And when they looked at how these activations, when they projected them onto this first principal component, what they saw was that statistically they were equivalent to a uniform distribution.
A uniform distribution.
Oh,
okay,
yeah.
and what does that tell us?
Well, it means that the way they're using this most important pattern, it's statistically the same,
Okay.
even though the specific values might be different.
Okay.
And then when they looked at the correlations between these first principal components for different AI scientists,
Okay.
they found strong positive correlation.
All right.
So this means that even though they have different internal configurations,
Yeah.
they're learning the same fundamental theory.
Okay. So the answer is yes.
It seems so.
Multiple AIs looking at the same system. They do agree on the underlying physics.
They tend to, yeah.
Awesome.
Right.
So now that we got that out of the way,
Right.
the paper goes on to explore something else.
Yeah.
And they want to know which theoretical framework the AI tends to prefer. So it's Hamiltonian mechanics, which is based on energy,
Right.
or Lagrangian mechanics, which is based on, it's a little more complicated.
A little bit, yeah.
But it's the difference between kinetic and potential energy.
Yeah, so it's like focusing on the total energy versus focusing on like the balance between what's being used and what's being stored.
Got it. Can you just remind the listeners about the difference between these two ways of describing motion?
Sure, yeah. So they're both powerful ways to describe how things move. Hamiltonian mechanics, it focuses on the total energy. So like the sum of, its energy of motion and its potential energy, its stored energy.
Right, okay.
But Lagrangian mechanics uses the difference between those two.
Okay, the difference.
So it's like the energy of motion minus the stored energy.
Got it.
And that difference, that sign flip, it actually makes a big difference.
Oh, okay.
Yeah, and the researchers, they wanted to see if the mathematical function that the AI learned, if it looked more like a Hamiltonian,
Okay.
Kinetic plus potential,
Yeah.
or a Lagrangian kinetic minus potential.
Okay.
And to do this, they fit the learned function to different combinations of those two types of energy.
Okay, so they're seeing which one fits better.
Exactly.
All right. And did the AI actually show a preference for one or the other as they got more complex?
Yeah, they found a really cool trend.
Okay.
If you look at figure 11A,
Okay.
it shows that for simple systems like the harmonic oscillator and the pendulum, M as S mostly learned a Hamiltonian description.
Okay.
Like over 90% of the AI scientists agreed on that.
So they're all using Hamiltonian for the easy stuff.
Yeah, pretty much. But then as they moved on to more complex systems like the Kepler problem,
Okay, the planets.
the planets,
Okay.
and the relativistic oscillator, there was a shift.
Okay.
MSS started to prefer a Lagrangian theory.
Oh, wow. So it's like once things get hard enough, they switch over to Lagrangian.
It seems that way, yeah.
That's so interesting. Any ideas why that shift might be happening?
Well, they think that maybe the Lagrangian way of doing physics is just more natural for how the data was presented to the AI.
Okay.
So Lagrangian mechanics, it often uses what are called generalized coordinates,
Okay.
which is kind of a flexible way of describing a system's position.
Okay.
But Hamiltonian mechanics, it often needs a more explicit definition of momentum,
Okay.
which might not be as easy to figure out from those generalized coordinates.
Okay, so it's like the math is easier with Lagrangian.
It could be, yeah. It might just be a more convenient language for the AI to use in this context.
So it's almost like the way we present the data can influence the kind of theory the AI comes up with.
It really seems that way, yeah.
That's fascinating. The paper also mentioned that for these more complex systems, the learned function also got closer to the actual Lagrangian function, right?
Yeah, that's right. Figure 11b shows this pretty clearly.
Okay.
And it suggests that not only did they prefer the Lagrangian form, but they were also getting better at actually, like, speaking the language correctly.
Okay, so they're not just choosing the right language.
Yeah.
They're actually getting better at it.
Yeah.
Okay. But how do we know that they're really capturing, like, the true essence of Lagrangian mechanics?
Right.
And not just coming up with something that, like, looks similar on the surface?
Yeah, that's a great question. So to really test this, they use this technique called constrained optimization.
Okay, constrained optimization.
Yeah. So basically, in Lagrangian mechanics, the acceleration of an object, it can be predicted based on how the Lagrangian function changes with position and velocity. So what they tried to do was see if they could mathematically transform the calculations that the AI network was doing into this standard form that's predicted by Lagrangian mechanics.
Okay, so they're like, can we make the AI's math look like the Lagrangian math?
Exactly, yeah. Can we translate it?
Okay, and could they?
Well, the results are shown in Table 2, and they were really impressive.
Okay.
They found a very high degree of agreement, over 90% in a lot of cases, between what the AI learned and, like, the mathematical structure of Lagrangian mechanics.
Okay.
And this was across all sorts of systems, including some that they, made up just to test it.
Sure.
So this really suggests that for these complex systems, the AI scientists are converging towards a description of physics that is fundamentally Lagrangian.
Wow. So Lagrangian mechanics might be a really good way to describe the universe.
It might be one of the more natural ways.
Okay. Now, the paper also talked about, whether these findings hold up for more, like, realistic higher dimensional problems.
Right.
The chaotic double pendulum.
Yeah. So for most of the experiments, they focused on simpler systems,
Right.
systems with just 1 degree of freedom.
Okay.
But they also trained mass S on the double pendulum, which is more complex. It's got 2 degrees of freedom,
Okay.
and it's chaotic.
Okay.
It's hard to predict exactly what it's going to do.
Right. Okay.
And figure 12 shows that mass S could still predict the double pendulum's motion pretty accurately.
Okay.
And the energy was conserved fairly well, comparable to other, specialized neural networks that were designed specifically for Lagrangian mechanics.
So even for a chaotic system, mass S is still doing well.
Yeah, it's holding up.
Okay. And did it still prefer a Lagrangian description for the double pendulum?
It did, yeah. Table 2 shows that as well.
Okay, cool. And they even went beyond the double pendulum, right?
Yeah, they briefly mentioned that.